This is incline plane, simple method. It's just a single triangle method, and the way I learned it, I figure a single triangle method is much simpler and easier to learn than a method that involves four triangles and they're all connected together. There's a few steps here, but they're all baby steps. First, let's just look at friction. We got a block here on the ground. We need a force to pull it in that direction to the right. The downward force, noted as F sub d, is the same thing as mg, mass times acceleration from gravity. If this is a tabletop, for example, there'll be a normal force pushing up that has to counteract that downward force. Otherwise, the downward force would push it all the way through the table and to the center of the earth. The normal force must equal mg as well, or mass times acceleration from gravity, so that those two forces can equal each other. If we're pulling this block across the ground to the right, we can imagine that there's some sort of tension scale in the rope that we're pulling on, and that tension scale tells us how much force we're pulling. Resisting that pulling force to the right is a force that pulls it to the left. That is the frictional force, which is the same thing as the downward force times mu, which is the coefficient of friction. But as you can see, downward force is the same thing as mg, which is the same thing as normal force. So all of these terms are interchangeable. So you have F sub d times mu, normal force times mu, mg times mu. It's all your downward force times the coefficient of friction. Just set your frictional force equal to your pulling force. For the frictional force, I'll use mg mu, and that'll equal the force of pulling. Bring this up right here. Isolate mu. We have the pulling force over mg equals mu, but this is also the same thing as the pulling force over the downward force. So if you wanted to measure this yourself, you could take any block or anything you want to pull, have a rope with some sort of tensile scale on it to tell you how much force you're pulling with. If you're having to pull with a very large amount of force, but the downward force is very small because it doesn't weigh very much, then you have big divided by little, so you're going to have a large mu, which is a large coefficient of friction. So the formula is just mu equals your pulling force over your downward force. Now for this single triangle method here, maybe this isn't so much as a proof as an explanation, but it explains it really well and it's super simple. Mg mu is your frictional force. I think it's easy to imagine if this block here is on a horizontal surface, you're going to have maximum frictional force. So the cosine of 0 is 1, which means 100%. So if we take mg mu, which is the frictional force, times cos theta, that will tell us how much our total frictional force is when we are pulling at an angle. Now imagine instead of cosine of 0, we have cosine of 90 degrees. So instead of this being a flat surface, horizontal, imagine it being vertical. So that would be 90 degrees. Cosine of 90 degrees is 0. Thus, there will be no friction as this block slides down with a wall next to it. The block may not even touch the wall. So a little bit of a jump in logic, but mg mu cos theta equals your frictional force. I'll use this here on the next page as we have a block sliding down a ramp. The frictional force pulling this block back, not allowing it to slide, is just mg mu cos theta. If theta is 0 degrees, we have maximum friction. If theta is 90 degrees, we have 0 friction. And so we just take the cos theta to get the friction of somewhere in between. Next, a little bit of a jump in logic. If you have a scale on this block right here, a scale, and you're putting a scale in front of this block to see how much force this block is pushing down. If this block is on a wall that's 90 degrees or vertical, you're going to have the full force of that block, so you're going to have the full mg, but you could also say mg sine theta, because sine of 90 degrees is 1 or 100%, so you'll have the full force of this block pushing down on you or on a scale. Then as this theta or this angle goes down to 0 and it's horizontal, put a scale in front of this block and you'll have 0 weight or 0 force pushing on it because the block is sitting on a horizontal surface. So you can imagine as your theta increases, then your sine of theta will increase and then your downward force will increase. So downward force sine of theta is the same thing as mg sine of theta. And that's the force of this thing sliding down. It's being opposed by mg mu cos theta. Let's take our net force. So you just take one minus the other. It's that simple. Pull out your mg. So you have mg times the quantity sine theta minus mu cos theta. Now we know that mass times acceleration equals force. But in this case, we want the net force. And let's isolate our acceleration right here. So we end up with acceleration equals mg times the quantity, sine theta minus mu cos theta, quantity over mass. Then mass divided by mass cancels. We're left with g sine theta minus mu cos theta, and that equals the acceleration. And I think it's easy to imagine that if you have no friction, then you can just look at g sine of theta for your acceleration from gravity. So I wrote here, this is acceleration without friction. So if you just have plain g by itself, that means it's falling vertical, which is 90 degrees. So g sine 90 is just going to equal g. So that is inclined plane, simple version, single triangle method. And that's it.